Welcome to Study Loop.
For this problem, we have two states. So state 1 is when disk B is at rest, and state 2 is when disk B moves with platform A. So disk B is now added to the platform and moves along with it. So in state 1, we can see that the platform A rotates with angular momentum I bar A times omega 1. In state 2, platform A moves with angular momentum I bar A omega 2, and the disk is now added to the platform and moves with angular momentum I bar B, where I bar is the mass moment of inertia for A and B, and omega 2 is the angular velocity. The distance between the center A and the center B is 0.12 meters. Since the radius of A is 0.2 meters and the radius of B is 0.08 meters. So subtracting the two, we get 0.12 meters. So the first thing we'll do is have a look at our moments of inertia. So our moment of inertia for platform A, I bar A, is equal to the mass of the platform times its radius of gyration squared, k squared. And this is equal to 5 kg into 0.175 meters, that's squared. And so we get moment of inertia to be 0.153125 kg meter squared. The moment of inertia for the disk, IB, is equal to a half mb, the mass of the disk, times RB squared. And so this is a half into 3 kg, the mass of the disk, times its radius, which is 0.08 meters, and that's squared. We get the moment of inertia of the disk to be 9.6 times 10 to the minus 3 kg meter squared. So now we have the moment of inertia for both the platform and the disk. So kinematics tells us that in state 2 is when disk B moves with platform A, the linear velocity of the disk B is equal to 0.12 meters. That's the distance between the centers A and B multiplied by angular velocity omega 2. So now let's apply the conservation of angular momentum. So angular momentum is conserved from state 1 to state 2. We'll take anti-clockwise moments about d. So if we take anti-clockwise moments about d, knowing that the angular momentum is conserved between the two states, we get that the angular momentum IA omega 1 must equal to IA omega 2 plus the angular momentum for the disk about d IB omega 2 plus the contribution by the straight line or linear momentum MBVB times 0.12 meters. So we can substitute some values into this equation. So we've calculated IA and IB. So this is 0.153125, that's kg meter squared. We'll just suppress the units for now, times omega 1 is equal to 0.153125 times omega 2 plus 9.6 times 10 to the minus 3, which is IB, multiplied by omega 2 plus the mass of the disk, which is 3 kgs, into VB, which is 0.12 times omega 2, 0.12 meters squared times omega 2. And so if we simplify and rearrange this equation, we get 0.153125 multiplied by omega 2 is equal to 0.20593 times omega 1. And so omega 2 is equal to 0.7436 times omega 1. And omega 1, the initial angular speed, is known. So this is 0.7436 into 50 revs per minute. And hence, we have found the angular velocity in state 2, omega 2, to be 37.2 revs per minute as required.